Right, hello everyone again. So let's have a look at isomers in organic chemistry. So we get two different types. We get structural isomers and we get stereoisomers. We're going to look at these two. Now, definition-wise, it's important that you note that structural isomers are molecules that have the same molecular formula but have different structures. So they look different. In essence, if you compare the IUPAC name, the names are different with structural isomers. So I'm going to show and talk you through each one. We get chain length isomers, position structural isomers, and functional group structural isomers. The second type is where, yes, the molecules have the same molecular formula, but they have different spatial arrangements. So look at the definition that I have. Isomers, stereoisomers are isomers that have the same molecular formula, but have a different arrangement of atoms in space. So, and we get cistrons, which is also termed geometric isomers, and optical isomers. Structural isomers with respect to chain length, this is literally, if we have our molecule of butane, C4H10, our simplest way to illustrate it is a straight chain. So 4 carbons in a row, straight single bonds, butane. Our chain length can be shortened by taking literally off the end and adding it as a side chain. So now our molecular formula is still the same. There's still 1, 2, 3, 4 carbons in there, and there's still 9, 10 hydrogens in there, but my name is different. So my structure is different. So it's 2-methylpropane. Right, so hopefully you've looked at the video on naming of organic molecules that I've posted. That will help you with the names of it. I will also, in this video, elaborate a bit on the names. Right, so let's have a look at our second of the structural isomers, which is position isomerism. So now we look at the molecule C4H9Cl. So again, a butane, but a chlorobutane. And where we put our chlorine depends on, or determines the position and positional isomers. Oh, got a bit tongue stuck in there. So if we have our chlorine on our second carbon, as illustrated in this first example, then 2-chlorobutane. Remember, naming, as I said, we first name our longest parent chain, 1, 2, 3, 4 carbons in there, butane. There is something weird happening in there. There's a chlorine group. And we number our carbon chain so that the chlorine has the lowest number, so it's 2-chlorobutane. If I want a structural isomer of this, I can change it. I can put my chlorine on my first carbon. Now I have 1-chlorobutane. We must add a number. Why? We add numbers to show that there's various positions my chlorine can be at. Can be either 1 or 2. Question: is this a possible isomer? The situation number 3? No, it's not. It's not. Because now, again, if we follow our naming rules, this is going to be 1, 2, and we sit with the same name. Our molecule is just changed around. It's not a different isomer, it's the same molecule. I've just drawn it from the other side. Okay, so make sure that you have your naming correct, because that's going to influence how you indicate and show your isomers with the position. Our third structural isomerism is functional group. And what did I do here? This is wrong. This is not a correct one that I wanted to show you. If we look at functional group isomerism, sorry, this happens sometimes. Functional group is when we interchange between two functional groups. So let's draw and my first one in there, and I need to change this now as well, is going to be ketones. So my ketones and aldehydes are two very good examples of functional group that are interchangeable. So not interchangeable, that are isomers. So if I look at this structure and I name it, there's 1, 2, 3 carbons in there. So again, it's because the AN refers to only single bonds between my carbons. But now I have this carbonyl group in there, and it is a ketone because it's connected to two other carbons. So ketone, and it's on carbon number 2, so propan, no, propan 2. It's got the molecular formula of C3H6O2. Right? What about my isomer of that? Well, we said we can do an aldehyde. Does it have the same molecular formula? Yes, C3H6O. Sorry, it's just O, it's not O2. Oh, I'm making silly errors in here. Okay. There we go. Because although it's a double bond, there's just one oxygen attached to it. So, make sure the molecular formula is the same. Even I make various mistakes throughout. Okay, so how do we name this? Again, 3 carbons, propan, and now my aldehyde can only be on carbon number 1. So we only give a number to a functional group if it is possible to have various positions. Aldehyde always on my first carbon, so this is just propan, propan, right? Propan, and this propan 2. So this is how functional groups are isomers of each other. Can you think of 2 others? Well, let me help you. We can also consider carboxylic acids and our esters. Those are also functional group isomers. Okay, so watch out for those. They're coming your way in questions. Stereoisomers. We get 2 different types, our cis-trans and optical isomers. So for our cis-trans is when we have a double bond and when there are 2 different groups attached to my carbon. 2 different groups attached to my carbon, and there's a double bond. Must be a double bond because if there's a double bond, there's no rotation possible. Right? So, how do we name something like this? Have a look at the 2 possibilities. And some of my hydrogens that is giving this away is the 2 groups attached to it, a methyl group and a hydroxyl group. Let's see where's my methyl and hydroxide group at the bottom. It's on the same side. If it's on the same side, it is cis, prop N1-ol. Look at this. En, like an ene, alkenes, because there's a double bond. Again, trans, it's across the double bond. So then it's trans, prop, ene1-ol. So propan, 1-ol, N. Alright, so it's just the writing of it. And yes, spelling does matter because if it was AN, it would have referred to single bonds and it would be wrong. You will find that in certain videos and textbook they talk about the EZ geometric forms as well. It's the same as cis and trans, it's just different namings that they use. Cambridge prefers the cis and trans, Right? I will elaborate on the E in Z a bit later on. It's just various languages and the names, and therefore the different naming. The last one that we look at is optical isomers. Now, optical isomers have this thing called a chiral center. What is a chiral center? A chiral center is a carbon that is connected to 1, 2, 3, 4 different groups. Then only, and only around a chiral center, we can have optical isomerism. Optical isomerism is when we can rotate our molecule. Remember the definition for stereoisomers? So, spatial arrangement, that's different. So we can rotate it so that when these two molecules are fixed like this, we cannot superimpose them. It's like your left and right hand. If you put it on top of each other, your thumbs do not match. It means it's not superimposable. Can't attach it. So, two things, very important. Look at how I've just drawn it. This is my mirror image. Usually in a question paper, they will give you a supply with space and ask to draw you the optical isomer of a specific molecule. After that, obviously, I ask you to identify the chiral center. You can play with this, but this is the easiest way that I'm showing. Yes, it is going to be in a 3D type of way, where the thick or arrow becoming thicker, line becoming thicker means it's coming towards you, and the dotted line means it's going away from you, and then the two straight lines are in the same plane. Just by giving the mirror image of it, keeping the bonds with your dotted line, you have your hydroxyl group, keeping your methyl at your line coming towards you, and the other hydrogen at top, and chlorine. That's a mirror image. This is a nice 2-mark question. Watch up, heads up, your carbon is attached to the bond, not your hydrogen. So if you draw a bond and you say H or CH in there, this is going to be marked wrong. This is impossible because my hydrogen can only have one bond attached to it, and it's actually bonded to my carbon in this one, if we consider this. So don't shift your molecule. Right? So what's the correct orientation? CH, if it's like that. Same with your oxygen. Oxygen can be bound to two molecules, to have two bonds to it, so oxygen and hydrogen. This is possible. Remember, oxygen has 6 electrons, has open space for 2 half-full orbitals, possible, but not your hydrogen. So be careful on how you draw this molecule. Okay, just be careful. Alright, so that's it for structural and stereo isomers. This is the very basics. We're going to practice this over and over and over in your worksheets and also end of chapter questions. Okay? Enjoy.